Hi all, welcome. My name is Arnab Biswas. I'm a data scientist at the Eco-Energy business of Carrier Global Corporation. Today I'm going to talk about automated feature engineering for large-scale time series data using two Python libraries, tsfresh and Dask. Let's start with the definition. In time series, we capture the value of a variable repeatedly over time, resulting in a series of data points indexed in time order. The most important characteristics of time series is the value of a variable at any particular instance of time is dependent on the values from the previous instances. That is, there is a natural temporal ordering in the data. Now, the most important characteristics of time series brings the biggest challenge, the temporal ordering. Traditional machine learning algorithms are not designed keeping time series data in mind. So if I feed a series of numbers representing a time series to a machine learning algorithm, probabilities are very high that the algorithm will not be able to decode the information hidden inside that temporal ordering. Then there are other challenges. For example, the nature or the pattern of the time series changes over time, making it non-stationary. Time series data may go noisy. Generally, in an industrial environment, we use sensors to capture time series data. If a sensor goes faulty, it starts picking up a lot of noise, reducing the signal to noise ratio. Often, what happens for any time series task, like a forecasting or classification, we have not one time series, but multiple time series. And these time series, they may have different sampling frequency or different length. Finally, time series comes from different domains. The nature or pattern of the data changes from one domain to another domain, from one use case to another use case. To address these challenges, we use something called feature engineering. In feature engineering, we try to capture the most important characteristics of a time series into few metrics. For example, here I have a long time series with 60,001 observation. I can start representing this time series in terms of few metrics like mean, median, maximum, minimum, etc. That way, I compress a raw time series into a shorter representation. And this is necessary. This is necessary for the machine learning algorithms, which may not be able to decode these numbers, but the machine learning algorithm may be able to understand the information extracted in the form of these features. Next, the question is, what are the features do I need? Generally, we start with the standard generic features, which helps us to summarize the data, and then we move into the domain-specific features. Again, within the same domain, the features which are relevant for one use case may be completely different from the features relevant for another use case. So as a data scientist, it's our duty is to generate as many features as possible, and then using cross-validation mechanism, select the most relevant features. This is where a library like tsfresh comes into picture. tsfresh is an open source Python library. Using tsfresh, we can automatically generate 750 plus features from one single time series. And the nature of the features vary widely. There are features which are related to descriptive statistics. There may be features which are related to the scientific background, like digital signal processing. And of course, there are features which captures the historical nature of the time series data. Out of the box, tsfresh provides feature selection mechanism as well. However, we are not going to talk about feature selection mechanism today. We are going to focus on the feature generation process. Next, let's extract few features using tsfresh. For this, I have picked up some data from a Kaggle competition called INGV Volcanic Eruption Prediction. The data consists of a large number of CSV files. Each CSV file contains 10 minutes of logs from 10 different sensors placed around a volcano. We call each CSV file as one segment. This is how the content of one segment file looks like. There are 10 time series. Each time series is associated with one sensor. Next, I pick up a bunch of time series and append them. I pick up a bunch of CSV files and append them in a pandas data frame. For the sake of simplicity, I pick up just two time series related to sensor 1 and sensor 4. This is how the aggregated data or appended time series looks like. It has data from various segments, and within one segment, the observations are sorted based on the column called time. Next, I pass these pandas data frame into the extract feature function of tsfresh, and tsfresh generates a bunch of features. What tsfresh has actually done, it has taken all the time series which are there for a particular segment and then generated all the relevant features and placed them in one row. As a result, my extracted feature data frame has one row per segment ID. For two time series, tsfresh has generated 1558 features. That means for one time series, it has generated 779 features, which is huge. Let's take a look at a few of the features which tsfresh has generated. Here are the features related to sensor 1. There are basic features like maximum and minimum, and then there are features, more complicated features like C3. To be very honest, I don't understand all these features, and probably that's the point. There may be features which are relevant for my task, but which I am not aware of, or which I have not been able to identify during my research works. But those feature works, and that's where tsfresh adds the value. We should note that tsfresh also generates features based on rolling data. Now, if the size of the time series increases, we start hitting two types of problems. One, large execution time, which is a compute bound problem, and we start feeling the need of large memory, which is a memory bound problem. To address the compute bound problem, we should utilize multiple cores or processors which are available in a CPU inside a single machine. If the resource available in a single machine is not sufficient, we should use distributed computing. To handle larger than RAM data, we should opt for one of the following options. First, we should try to slim and trim the data so that it fits into the memory. If that doesn't work out, we should upgrade our RAM to a larger size. If that's not an option, we should use something called out-of-core computing. Out-of-core computing is a concept used by Dask, so let's try to understand it. In out-of-core computing, the data rests in the hard disk. At any point of time, we pick up one small portion of the data or few partitions of the data, load it into the main memory and do the computation. Next, we come back and pick up few other partitions from the hard disk, load it into the main memory and do the computation. And the process goes on. At any instance of time, we are not loading all the data from the hard disk into the main memory. That's how out-of-core computing handles larger than RAM data. If none of these options are working out, then we should use distributed computing. What are the challenges which we face while doing data science with large data? Popular libraries like NumPy and Pandas, they are not designed to scale beyond a single core or processor. They are not designed even to scale beyond a single machine. If I have a data which is larger than RAM data, then these libraries cannot be used. These libraries expect the data to be loaded into the RAM for computation. This is where Dask comes into picture. Dask is an open source Python framework which parallelizes the Python ecosystem. Using Dask, we can utilize multiple cores which can be in one machine or which can be distributed across multiple computers. Dask handles large data using out-of-core computing. Dask works well in multi-node cluster or 100-node cluster. At the same time, Dask works in a single instance VM or on a laptop. The good news is, out of the box, tsfresh addresses the compute bound problem or the memory bound problem. If the data fits into the main memory, that means if we can load the data into a pandas data frame in a single machine, tsfresh utilizes multiple cores available in that machine. tsfresh can distribute the feature extraction process to a clustered environment. tsfresh handles larger than memory data utilizing Dask and PySpark. However, I'm not going to talk about all these today. Rather, I'm going to talk how I utilize best of both the worlds. I use tsfresh to extract the features from time series data, and I use Dask to parallelize the feature extraction process as well as to handle larger than memory data. Let's start with the basics. This is the Dask architecture. The client is an interface using which user can interact with a Dask cluster. The Dask cluster consists of a scheduler and multiple workers. The scheduler actually doesn't do any computation. It distributes the tasks to the workers, which does the computation, comes up with the final result, sends back the results to the scheduler, and the scheduler in turn sends back the result to the client. The scheduler and worker, they may be located in one machine or they may be located in multiple machines. If the client, the scheduler, and the workers are located in one machine, we'll call that as a local cluster. Here, I have created a local cluster in this VM with 8 workers. Next, I have created a Dask client and connected that client to the cluster. Now onwards, any computation related to Dask happens in this cluster by these multiple workers. Next, I have asked Dask to read few CSV files which matches with this particular regular expression. Looks like there are 4 such CSV files, and Dask reads these files very quickly within 119 milliseconds and returns us back a Dask data frame. But in reality, Dask has not actually read any CSV file yet. It has created a plan, which we call as task graph, to read the CSV files. The Dask data frame looks similar to a pandas data frame. However, it has 2 additional things. One is called partition. It has 4 partitions and it has 4 tasks. To understand what is a partition, we have to understand how a Dask data frame is constructed. A Dask data frame, represented by the gray color, is nothing but a wrapper on multiple pandas data frame. The pandas data frames are represented by black. Each pandas data frame, in our case, is associated with one segment or one CSV file. Since we have 4 CSV files, we have 4 partitions. Next, if we invoke the method called visualize on this Dask data frame, we can see the task graph. This is the plan which Dask have to read all the CSV files. One of the worker will pick up one CSV file, load the data into a pandas data frame. Now this happens for all the 4 CSV files by multiple workers in parallel. Next, we'll see how we can parallelize a custom Python function using Dask. This is a custom Python function, and I invoke this custom Python function on this Dask data frame consisting of multiple partitions and parallelize the process using map partitions API. This is the corresponding task graph. So one of the worker will pick up one of the CSV file, load the data into the main memory in the form of a pandas data frame, and then invoke this particular method or function on that pandas data frame. And here at the end of the process, we'll have the result available. Now this happens again for all the 4 CSV files by multiple workers in parallel. We call this methodology as embarrassingly parallel. I'm going to use this methodology to parallelize tsfresh's extract feature function. Finally, when I invoke the method or function called compute, then Dask actually executes the task graph, computes the result, loads it into a non-Dask data structure like pandas or NumPy, gives us back the result to the client. Next, let's try to parallelize tsfresh's extract feature function using Dask. Here, I'm asking Dask to read all the CSV files which are there inside the train directory. There are 4431 such files, hence the Dask data frame has 4431 partitions. This is the custom Python function. This custom Python function is nothing but a wrapper on tsfresh's extract feature function. By setting n underscore jobs to 0, I have shut down tsfresh's internal parallelization mechanism and I have allowed Dask to take over. Finally, here I am invoking the custom Python function on this Dask data frame and parallelizing the entire process using map partitions API. At the end, I invoke a method called toParkway. The moment I invoke this method, Dask starts executing the task graph. Dask for each segment file, Dask loads them into the main memory in the form of a pandas data frame, extract the features, and then writes the extracted features back to the hard disk. Next, let's take a look of the Dask dashboard. Generally, it takes some time for the workers to pick up the tasks and starts executing it. Let's wait for the workers to start working. Here, each horizontal line represents one worker. There are 8 workers and hence 8 horizontal lines. It shows each horizontal line shows the tasks which each worker is executing. Different tasks has different colors and the name of the tasks are shown here. Next, we move to the workers tab. It shows that there are 8 workers. The CPU usage of the workers are pretty high, above 90%, but the memory usage is considerably low. This is because of the fact that Dask is doing out of core computing. So one of the worker at any instance of time is picking up one of the segment files, loading it into the main memory in the form of a pandas data frame, then using tsfresh's extract feature function, extracting the features, and finally writing those features back to the hard disk. Then the worker goes back and picks up the next segment file and it continues the process. That is how Dask is parallelizing the entire process by using multiple workers, and at the same time using out of core computing, Dask is handling larger than memory data. With this, we come to the end of this session. Here are few references which I have used, and this is the place where I have saved the slide as well as the code. Hope you have enjoyed the session. Thank you.
Everywhere and no time to think? Well, you might be probably thinking that what actually this weird topic means. Well, this is about common misconceptions and problems that we day to day face in data science world. Let's start with a little bit of introduction about me. My name is Aman Sharma. I'm currently the co-founder and chief technology officer at Twimbit. Twimbit is a research-based company in Singapore which creates interesting and interactive insights using latest technologies, and we create research joyful and fun to consume. Also, I'm a member at deeplearning.ai. I love mentoring students and also I'm a hardcore serial entrepreneur. I define myself as a tech generalist in the fields of AI, cloud, and web. So, you might be probably lost in the huge ocean of data, wondering always what that magic of wise wisdom thing that could come out of this probable data that could help you make effective decisions and improve the overall experience, data science experience in your team. Well, to understand this before, we should define the clear goals between what's the difference between data and insights. So imagine yourself wandering and trying to look for these insights. And what if there was a lighthouse that could point you in the right direction? The pearls that are floating around this ocean, which we can define as the insights, are the ones that you are actually looking for to make good decisions and improve the overall life and experience of your product. Well, this presentation is exactly like this lighthouse, where I'll be trying to cover important things that could help you find these insights out of the huge pool of data. So, in this talk, we'll be covering important problems that are occurring with today's data science issues and also some simple solutions to them. We'll be covering a new strategy, that is data science sprints, to cover our data science projects. Also, we look into two different approaches of no code versus code for data science. And also, we'll see how you can effectively use visualizations to improve the delivery of the content of a data science project. We'll also see how you can create dashboards to convey important information and message through a very transparent and easy to consume reports. Also, how we can document the whole process so that we can improvise and learn from what we are doing. So let's start with a couple of problems. The first problem that occurs in any data science project is the clarity of goal. It's very important to keep everybody aligned to the same achievement and the same goal to improve the overall service, but often you would see people losing the track of the whole data science. And also people will be asking probable questions like why we were here again and what is the main goal of the team. Everybody in the team would have a different perception of what actually is going on into the team. This kind of creates chaos and ultimately leads to wrong outcomes which you never imagined, leading to overall low return of investment. A probable good solution is basically identifying the goal and communicating the whole goal with the team. We'll see in the other slides of how you can actually identify the goal and communicate it with the team. Another problem is poor planning. It leads to situations, chaotic situations, and often abandonment of projects. Also, sometimes it leads to wastage of resources and time. You'll be missing deadlines. Maybe the results you are getting are not good enough, or the resources that you are using, you are not able to predict them, always questioning that whether you have less resources. And the probable solution to this one is also to come up with a better structure of the project, having less deliverables to have measurable outcomes, and also have strict timelines so that you never miss a deadline and always deliver on time. Another problem is dirty data. Due to now vastness of data and also sometimes corruptness in the way data is stored, you might be experiencing this problem of having bad data at the same place. Now, the symptoms to this problem is again you are spending too much time on data pre-processing rather than making actual decisions. Also, the ratio between the data, the overall data of the ingestion and the insights you are able to get is not that good, ultimately leading to poor results. The solutions to this problem is also again using advanced tools which can help in better clean data, or maybe in the ingestion tools could be better, and also improving the source of how you're getting the data. Another problem that people face is divided into these four sub problems, in which you have technical challenges leading to tools limitation, resources, or problem in having the right talents, and privacy concerns have been a rising issue too. Well, due to this, oftenly you will see in your team, you will question yourself whether you have less number of people to do the job. You will not have a lower turnaround time. You are not able to complete the project on time, of course. And also the system to create the whole data science project is not as efficient. Also, the transparency between the whole team is not that good, and you're not able to communicate the overall value in the whole team. Now, you can solve this problem by modern solutions like no code or documenting your things properly and also bringing a little bit of transparency in the whole project. Another problem that people have is the complexity of data science. Not many people understand what data science actually is and how actually it should be performed. This leads to not very efficient methods of representing data, and also it's not able to, make a clear vision in the whole team, hence making it totally ununderstandable with the team. Symptom for this one is also unreadable data, poor decision making, and often thinking even the existence of a data science team in the company. So again, using no code, having better visualization, and having good feedback system can solve these problems. Last but very important problem that people face is silos inside the company, where the actual decision makers are not able to see and interact with the data science team. This leads to not a good communication between the two departments, whether it be marketing or sales, leading to lower growth of the whole company, and then questioning the intent of data science team, having less importance of the data science project at all. This again can be solved by the problem solutions such as dashboarding, automating the whole process, again having good feedback system and documenting the whole process. We'll cover about all these things in our upcoming slides. So the sprint solution that I was talking about, actually this is inspired from the book Sprint written by Jake Knapp. The whole data science sprint can be divided into four main sections: defining a clear goal, planning well about the project, executing the project, and then testing and improvising. In the clear goal, you are actually looking towards introducing the project to the team. With the past mistakes and lessons that you have learned, you should introduce the project to the new people of what you're actually trying to do. Then you should also define a long term goal. What is the long term objective that you are trying to fulfill with the team? Then you should set some clear questions that actually defines the questions that you want to answer in the team. These are more granular goals like investigating the ROI, or maybe investigating the overall click around time. It depends upon the project. Then creating a map of the whole problem in a very easy and understandable format, like a flow chart in which if one thing is happening, what is leading to the another thing, or what is leading to the third thing, something like this. Then, after you're done with clearing the goal, you should directly jump into talking with some experts or reading some existing insights on how somebody else has done their project. Then you should pick up a small scope or target. Less deliverable means high chances of you achieving that goal. So complete one target and then move towards other. Then create something called as how might we notes, in which you ask everybody to give their own opinions about how you can solve the particular problem. Pick a approach, whether it should be a code or no code approach. Then create a flow diagram of a kind of a pretty neat diagram to understand how this thing works. Set clear deliverables in the execution part, set a timeline for the whole team, and try to stick towards it. Divide the tasks so that everybody has clear responsibilities. Meet regularly with the team to understand if everything is going smoothly. Then, after you're done with the whole project, then you should move towards the test and improvise part, in which you should first create an MVP or a test report and present these findings to the team. So then just try to collect the feedbacks about what they think without explaining them much about the data science, so that it becomes even simpler for them to understand in the future, even if you are not present. Improvise over these feedbacks, document these learnings so that it can be again used in the next iteration of the sprint. Then important step in this process is creating good diagrams. Diagrams are very important to bring thought clarity in the team. It helps you set realistic goals and achievables, and also set realistic timelines. It also helps you estimating in resources. The process of creating diagrams is simple. Lay out the important component of the whole project and list down what this project will use as additional sources like Python or script X or maybe a dashboard Y. And then try to connect how the three things connect together. Remember, the whole goal of creating diagram is to make everybody clear on the approach. The next one is choosing an approach. It can be code or no code approach. Both of these approaches have their own pros and cons. Where code has high flexibility, a huge scalability scope, and high availability of functions that you can use. At the same point, it's very difficult to learn, and less people know actually about how to write data science code. and also the talent acquisition is not that good, leading to creation of silos inside the team. And again, the whole project or the model is so complex that non-technical people can't understand them. On the other hand, no code is pretty fast. The learning curve is pretty small. It's fun and engaging to do because it's mostly drag and drop. It increases the productivity because you don't have to deal with other problems like data processing and stuff like that. And also, it's open to the whole team. Even the non technical people can come together and add their own data science projects or opinions. The cons to this approach is that you are not having much flexible options to choose between the strategy or the techniques. Also, the sources of choice of ingestion of data are limited to what the data science, the no-code tools actually offers. Hence, creating a dependency on the whole system of whatever the application offers, you can choose that only. The scalability of the project becomes far less possible when you move towards bigger data or even variety of data. Let's look towards common code tools. You might probably know about Python, the conference that we are attending today. Also, popular tools are like R and Scala. Then the other category of tools are querying and analysis tools such as SQL, MATLAB, and BigQuery. BigQuery has been a popular tool in recent days to do queries on big data on Google Cloud Platform. Then there are a whole lot of application suite that covers A to Z applications to create an end-to-end data science platform such as Apache Spark, BigML, and Hadoop. The other category of tools is no code or low code tools. Popular ones are used to create dashboard and reports like Google Data Studio, Tableau, and Power BI. Another one is an easy drag and drop way of creating data science flows using tools such as Xplenty, Intersect Labs, or Data Robot. Then there are also tool category which creates end-to-end data science flow such as obviously AI or Gyana. So this makes you question how you should decide whether what technique you should choose. So the matrix is pretty simple. If your functional requirements are low and the speed you are looking at is fast, you want a huge turnaround time, then you should definitely check out the AI solutions. Even if the speed of implementation is slow, you can yourself dive into this, create individual projects, and try out what a no-code data science project looks like. But if the functional requirements are high, then only you can use code techniques because that will offer you more flexibility and more sense of achievement. Another important part is how you communicate with the data, and you use visualization for that. Here is an interesting flowchart that you can use in order to decide what kind of chart you should use for what kind of variable. I'll leave the link to this whole diagram so that you can come back later and use it as a kind of a playbook or cookbook to actually do your data science project. I have added a couple of more instructions about what different charts means, so you can actually go in deeper and understand what a particular chart does for what kind of data. The next step in the journey is to dashboard the whole process. This step is actually to make your findings and shareable with everyone. So the first step is collect all the visualization for whatever charts, the whatever objectives you are trying to deliver. Then organize these charts into a very much organized diagrammatic dashboard view, something like how you see Jarvis dashboards, right? So that it's very easy and convenient to understand the data at one step. Then automate and schedule the process of revisiting this data or automatic collection of this data so that you don't need to interfere and manually create these reports. At the end, share the access of the whole dashboard with everyone so that everybody can come anytime, don't need to bother you again and again, and see the data themselves. Common tools to do dashboarding are such as Apache Superset, which is a very good dashboarding tool, Apache Airflow to create DAGs and ETLs. GramX is a whole suite of different tools to create data ingestions and dashboards. Plotly Dash, another platform to create dashboards, and Amazon Quick Insights. The next step in the journey is to create a well-defined document. The document helps you learn from your feedbacks and improvise the whole step so that the next time you are doing the sprint, you are able to see what were the problems in the last sprint and you are able to better perform the job in the next iteration. So create a shared document. It can be an Excel file, a Word file, whatever you want. I prefer to use something like a tabular structure so that you have more availability of columns. Then add the progress at each step. Whenever you think you are doing something in the data science, add it as a step and mark what is the overall progress that it's going on into the project. Add all the findings during your test and improvisation section chart of the sprint, and add these findings next to the progress. Then collect feedbacks, list down these feedbacks, and then you are good to go. Share this document also with the whole team so that anybody can come back and see what is actually going on into the whole data science team. Common tools to do documentation includes free tools like Excel, Google Sheets, or even Trello. But I personally am a fan of Monday.com and Airtable because they make the data logging so simple and easy. So that's pretty much about it. We covered a lot of stuff. So, well, there is a lot of things on the plate. I'll share this diagram again so that you can easily revisit and, perform the checks as you go in your data science project. To quickly summarize what we went through today were common problems, some common things that are causing problems in the current data science projects, how we can solve these problems using a technique called a sprint, where we also saw how you can create diagrams, which are very interesting way to communicate your idea and goal to the whole team. We also saw two new approaches, which not new but existing approaches, code and no code, where we also see how you can decide between these two depending upon what kind of project you are doing. We also saw how you can create visualization, what kind of charts you should use, and also how you should create dashboards, which is a very convenient way to share the progress with everybody. At last, we saw how you can create documents and how documents can help you improvise the whole data science step. So that's pretty much it. So that was about data everywhere, no time to think. Well, data and insights everywhere and all time to think. Thanks for your time. I hope you like the presentation, and if you do, please give me your feedbacks at